Neuromorphic computing is something genuinely new and different in comparison to the classical computing. The key idea is to mimic the way the human's brain works, because human's brain is one of the most efficient compute engines we know. In our traditional compute, so-called von Neumann architecture, the main bottleneck, so the main energy waste, is the access to memory. While in our brain the memory is distributed, it means every computing node in our brain gets its own local memory. The way to replicate the brain is to initiate these artificial neurons and artificial synapses a million times with localized memory. Such neuromorphic, so brain-like processors are really beneficial for edge AI applications. For instance, for applications like smart home and object recognition and many more. Actually, older generations of smart home devices like Alexa sense your input and then they send the data back to the cloud where it's processed. And then you get your result back to the device. Moving AI to the edge instead of cloud has many advantages, and one of such advantages is privacy. So your talks to Alexa do not need to be sent to the cloud to be processed. However, moving AI to the edge also requires really low-power AI processors, especially for battery-powered applications. In my opinion, edge AI is the future, and the neuromorphic technology is the key to make it possible. Now, such a neuromorphic chip is actually already available. It is Akida 1000. Akida is a Greek word which means spike. So, Akida processor literally means spiking neuromorphic processor. The exciting thing here that Akida chip has already moved from research phase to the production and sales. This year, they fabricated their first Akida SoC in 28nm TSMC technology, and this chip has already been delivered to the first customers.
We didn't start to say, let's design a neuromorphic solution first. We said we want to solve the edge AI problem, and it has to be small, and then we realized that the neuromorphic solution can be small.
And from the talk with brain chip founders, I realized that the way they quantify the chip performance is power consumption per application. For instance, for those applications like gesture recognition or object recognition, it consumes as low as 100 microwatt, which means it can run on a small battery for like half of a year. And the key feature here is one-shot learning.
Now, our learning is something similar to what how the brain learns. Brain learns by looking at patterns in repeating spikes. It's called STDP learning, synaptic time independent plasticity. We have the same principle. We implement that in hardware on our chip, so you can have one-shot learning. We can just take one sample and make a model out of that, and the sample will have different patterns because we have cats and dogs and tiger and elephant differentiation. All that can be done with one sample.
I watched some of their demos and honestly it looks kinda impressive, because you can show it just one picture of tiger and then AI is able to recognize tiger. Well, usually you need to show hundreds of pictures or thousands of pictures of tigers to train AI to recognize it. However, I'm really wondering how it's gonna work in a real environment where background can be noisy, blurry, too dark, or objects are moving, but we will see. The cool thing is, Akida can smell and taste. Here, Akida chip is testing wines, and it can actually distinguish between different types of wine. We humans identify patterns in everything, in language, in personalities, and even in pain. Every piece of data, brain is processing, looking for patterns and responding to patterns. And the Akida chip works the exact same way, so accumulating lots of patterns. Here, the sense data is processed directly on the chip and used for incremental and autonomous learning. So to say, adapting to the local environment in real time. They're not only selling separate chips or platforms, but the IP, so RTL code as well, which means other companies can license their IP and integrate HAI into their chips and then manufacture it. Recently, I read that Japanese mega chips will incorporate BrainChip's HAI into their ASICs. The application space of the Akida processor is enormously large. It can be used in cars. On the top of usual AI for ADAS, Akida can be used, for instance, to identify a driver and to adjust the car environment and infotainment system for each driver. Also, it can listen to an engine and then identify some sound patterns or something which sounds odd and then give a feedback to driver. Recently, I read that Akida will be used for voice assistance in Mercedes, for instance in AQXX cars, which is right now a concept car. And guess what? Their stock has just skyrocketed. Actually, I bought their stocks when it was like 0.6 or something, so it's doing really great. It's more than doubled. And of course, smart home and other IoT applications like Home Assist, various sensors and security. Actually, it is a really big market for HAI chips. Worth mentioning, Akida is a fully digital chip. This chip is fully scalable. It is easily scalable below 28 nanometers. And this will bring them to better performance and even lower power consumption.
Having a digital, our IP can go either to 7 nanometer or 65 nanometer, whatever the sensor data is. We can embed our IP into the sensor process, the sensor technology. It could be a 40 nanometer, 65 nanometer, or it can be 7 nanometers. We are process agnostic. So by keeping it all digital, we actually let people choose. Our first implementation 28 nanometer. Our next generation is actually in 22 nanometer. But somebody else wants to do, NASA wants to do a chip to put it on the satellite. That might be 90 nanometer because they want some alpha particle effects and all that. So we are process agnostic. So IP has really become truly scalable and process agnostic by keeping it digital. See, by the way, we have our power numbers that I told you about are for power for 28 nanometer running at 0.9. Right. If you go to 7 nanometer, the voltage will be 0.5 and things like that. Yeah. The scaling will be lot more scale it down. So it will be it will process the process scaling will apply to our power scaling.
Essentially, you can imagine this chip as a large cloud of gates, which consists of artificial neurons and artificial synapses. This is approximately how artificial neuron looks. Neuron accumulates signals, then performs so-called leak, integrate, and fire, and then send output to the next layer, so to the next neuron. These operations are independent of time and space. All of this spike communication and signaling is happening asynchronously, so just like in our brain. And this chip is processing spikes, so only spikes. And in this way, it processes much less data in comparison to the traditional AI accelerators, which are just doing math. In biology, it's not so simple because each neuron has different structure, and the structure defines the functionality. So in our brain, the structure of the network is the algorithm. And it is so interesting because here it is impossible to distinguish hardware from software. So biologically, it is a different way of doing computations than just writing a code on Python and mapping it to some hardware which is independent of the Python. At a higher level, Akida chip is an SoC, system on chip. The AI part of the SoC consists of 80 NPUs, neural processing units, with total 1.2 million virtual neurons and 10 billion virtual synapses. Each NPU comes with 100 kilobytes of SRAM memory to store weights and intermediate data, and it is networked with other NPUs into an on-chip mesh. The AI is built around a spiking-based model, which means it fires when a certain threshold is reached. And the energy efficiency of these CNN operations, so convolutional neural network operation, is much higher in comparison to a CPU, GPU, or even AI-tailored accelerator. It also integrates a Cortex M4 CPU, and on top of that, there is a bunch of interfaces like USB and PCIe and others to hook it up with different sensors, as well as to scale the system up. So to build a multi-chip Akida array in case more NPUs are needed. What's important, you can program this chip using TensorFlow and Python. So traditional state-of-the-art neural networks can run on this Akida chip. Of course, there are large AI accelerators like Google TPU v3, Google TPU v4, NVIDIA GPU, Cerebras, and so on. But this is another story because those are intended not for HAI, but rather for in-cloud compute. And these machines, of course, burn tons of power. Then there is Intel's Loi and Loi 2 chips, which are also fully digital neuromorphic chips, which I discussed in my previous video. What differentiates your HAI technology from other HAI chips out there? Because, there are also, for instance, Intel Loi chip, which is also neuromorphic and which is also fully digital. So what is the key difference between your chip and, for instance, Loi chip?
Very good. So let me first say that what we do is our hardware is neuromorphic. That means it basically only processes spikes. And again, if you look at the way the synapses are and the brain neurons work, each neuron has hundreds of synapses, thousands of synapses connected to it. It does integration of the weights. We do something similar. Calculating whether there will be a spike for the next layer fundamentally is no different than what IBM neuromorphic, the 2-North does, or Intel Loihi does, or what we do. The difference in what we have is what we did is actually to solve the problem. We actually introduced a new concept called convolutions in event domain. That's the difference between us and IBM 2-North and Intel. So what I mean by that is, if you look at a standard CNN, let's say MobileNet V1, what are you doing? You're taking image data, HD image and things like that. Then as you go through convolution, you're trying to reduce the dimensionality of the network to really extract features. What we decided, we first take the same frame and convert we get an RGB image first, like 8-bit data for R, G, and B. We do a traditional convolution on it, and as soon as the result of that, we actually encode everything into spikes. And now, what we're doing is we are doing convolutions in event domain on those spikes that happen, where IBM and Intel don't do that. So our claim to fame is, because we approached it directly and said, we want to allow a CNN also to happen in event domain. So I call deep learning, so DNNs are deep learning networks, right? So when we convert the deep learning CNNs into a spiking neural network, our chip actually has on-chip data to spike converter. And then we actually do convolutions on those event domain very efficiently in hardware, while IBM 2-North or Intel also can do convolution, but for them, because they are basically just neuron and threshold and things like that, the amount of core that Intel or IBM have to use to do a convolution in time domain is large. But doing a convolution in event domain is what gives us the small size and low power. And there are examples of neuromorphic computation that can be done on take the same data set and either do it on IBM 2-North or Intel Loihi or on our chip. Our chip always uses very low amount of hardware, does it very efficiently because of our uniqueness of doing convolutions in event domain for traditional audio or video samples.
The trend is artificial intelligence chip market is projected to reach $114 billion by 2026, growing by 43% from 2020 to 2026, and this is huge. Right now, we are entering the era of HAI, and Akida chip is one of the front runners there. It will basically enable compute at edge at 1,000 times lower power consumption or even less. It's just like our brain, is the most efficient compute engine in the universe. So emulating it seems to be the right way to go. If you want to learn more on neuromorphic computing, check out my first episode on it, and I will add some links to the cool lectures on neuromorphic computing, which I watched and enjoy. So if you want to dive deep into the neuromorphic computing, I will leave links in the description below. Anyway, thank you for watching, and I will see you in my next video. Ciao!